Hello, everybody. So, what we're going to be looking at today is section 5.1 in your book, which is mathematical induction. Now, just a few comments about this. So, before we start, number one, um, there are typed up notes for this same section, but I'm handwriting these because I think you need to see somebody write it out like by hand in order to understand what's going on. So, but there are typed notes if you like those on Canvas. And then just a note about the topic here. Well, mathematical induction, section 5.1, is just the start of an entire chapter on mathematical induction. Okay, so it's really super important that you spend some time understanding it now before it gets trickier. Okay, so yeah, so we have probably four sections of this on induction. Uh, Learn it now. Okay. Start the homework early. Don't wait till the last minute, uh, or you'll be in trouble. Okay. So, yeah, with that said, let's go ahead and get started. So, intro. What is mathematical induction? All right. So, what is it? So what mathematical induction is it's a proof technique, of course. That's not of course, you maybe don't know that, but it's a proof technique that works for proofs that generally, at least in this section, are going to be structured like some property is true for n equals 0, n equals 1, n equals 2, etc. Um, so a proof technique that works well for we'll say prove property P holds for um, like n equals 0, n equals 1, n equals 2, etc. Like that. Okay. Um, and that's the main idea that you want. I mean, that's not quite 100%. I mean, that's obviously not precise anyway, but what you can do is you can extend this to other situations other than this basic one that I described here. But certainly in the first two sections, it's going to be like n equals 1, n equals 2, n equals 3. And, by the way, the like n equals 0 doesn't even matter. Like it doesn't have to start at 0. You could start at like 5 and go n equals 5, n equals 6, n equals 7, etc. And you'll see why that is momentarily when we talk about it in more detail. But so it's a proof technique, and so we're going to be doing proofs. What's the idea of it? So I'm going to give you the idea of induction before we, write it out mathy. So here's the idea. Suppose you have somebody who wants to climb a ladder. Okay. Maybe it's you. Suppose you want to climb a ladder. No, I'll say a person. Okay. You have a person that wants to climb a ladder. Now, what if that person um, knows how to get on the first step, but he does not know how to go from one rung to the other? Um, if he Why the he? I don't know. If he can get on the first step of the ladder, if he can get on the first step of the ladder, but does not know how to go from one rung to the next, then he's stuck. Does not know how to climb from one rung to the next, he's stuck. Right? So you got this ladder, terrible drawing coming up. Right? So you have a ladder like this, and you have a guy, and he can get this far. He's got one leg off. I don't know why. But he can't climb because he does not know how to. Not know how to climb from one run to the next. So what's that mean is, he wants to go up, but he can't because he does not know how. Right? Now consider another situation. In this other situation, now consider a person that does know how to climb from one rung to the next. So he does know how to climb from one rung to the next, but mounting the ladder is tricky. So he does not know how to do that. But does not know to get on the first rung. Right? He also can't climb the ladder. Right? So you still got your ladder, but now you got your guy and he's over here, and he would be able to climb the ladder, right? This is okay. He would be able to climb the ladder, but he does not know how to get on the ladder. So, like, in order to go from here to here, that's what he does not know how to do. Right? So, either way, you've got a guy who can't climb the ladder because either he does not know how to get on the ladder, which is this guy, he does not know how to get here, or you have a guy who knows how to get on the ladder like this, but he does not know how to go up the ladder. Like this guy could go up the ladder, but he's not on the ladder, right? So you've got this situation where in both of these cases, you would not be able to climb the ladder. Okay? And so what induction is the idea that if you actually had somebody who knew how to do both of these things, then they would be able to climb the ladder. So if you had a third person, so now consider a third person that knows how to get on the first rung of the ladder, and also B knows how to go from one rung up to the next rung. So in that case, they'd be able to climb the entire ladder. this person and climb all the way to the top, right? Because you've got this person over here. This person knows how to do this, right? He knows how to go from here to here. That's step A. And then step B says he knows how to go from one rung to the next. And that's all you need, because if you're on one rung, right, then from here to here, that's one step of B. And then from here to here, that's another step of B. And then another for B, then another B, and then another B, right? As long as you know how to go from one step to the next, you just keep climbing the ladder. And so you're going to get your guy all the way up here. So that is the idea behind induction, actually. So you need two things. You need to be able to start somewhere, get on the ladder, and then also once you're on the ladder, you need to know how to go from one step to the next step. Okay, so let us say what mathematical induction is. Okay, so formally, or more formally at least, here's what it is. Right, so suppose you have some property you want to prove. Suppose, I'll write it like this. Suppose we want to show we want to prove P of n. So I'm saying when I say P of n, I mean true. So I'll even say that. I'll say we want to prove P of n true for all n equals 0, 1, 2, 3, dot, dot, dot. Okay. What you do is this. If you show two things. Well, what things? They're exactly the same as the things here. You need to be able to get on the first rung of the ladder, and then we need to know how to climb. So the first thing is, how do we get on the first rung of the ladder? What does that mean in terms of this proof, right? So the first, to get on the ladder, what that means is we're supposed to be showing P of n true. Well, the first n is, in this case, n equals 0. So if we can show P of 0 true, that would be the first rung of the ladder. The first P that is true is the first rung of the ladder. So if we show two things. So this is called the basis step, by the way. It has a name, basis step. Show P of 0 is true. So you have to do math to do this. Show P of 0 true. And then we also need, what's the second part? How to climb from one rung to the next rung. How to climb from one rung to the next rung. What's that mean in math? Well, what that means is if, like, suppose we knew that the property was true for P equals 2. So like P2. So if P2 was true, and somehow the fact that P2 was true made it force P3 true. So if P2 true implies P3 true, right, then that would get you from one step to the next step. And if it was true in general, any step implies the next step. That would be the equivalent of climbing one rung of the ladder, right? One step implies the next. One step implies the next. One step implies the next. Okay? That's the idea. So what is it down here? Well, it's pretty much what we just said. So basis step, show P0 true. Induction step or inductive step, I'll probably use those interchangeably. There's not really standard language for this. I mean, one step is basis and one step is inductive, but basis, inductive, induction, whatever. Same thing for basis. Like I'll probably write base step a lot. Does not matter. All right, inductive step. What are we going to do? You need to show basically this. P of k true. Now, I'm using k instead of n because n is kind of like our standard variable, and then k is going to be the one that we're plugging in here. You'll see when we do a proof. So show P of k true implies P k plus 1 true. All right, and that's it. Okay, that is induction. Because once you have both of these, then this will get you on the ladder, right? So like your ladder in this scenario here is still a ladder. So the idea here is your ladder is simply like P of 0, P of 1, P of 2, P of 3, like, and so on, right? Up the ladder. And so what's going to happen is the basis step is going to get you here, right? But then the induction step says, well, if P of 0 is true, then that must mean P of 1 is true. So that would get you from here to here. But now P of 1 is true. So P of 1 of true implies P of 2 true. And then that takes you one more step on the ladder. And then if P of 2 is true, then P of 3 is true. Right? And so in this manner, you just keep climbing the ladder using that inductive step. So you need the basis step to get on the ladder, and then the inductive step just takes you the rest of the way. Okay. Now the point is that you don't have to do that. Like what I wrote in pink, you don't write. You just write the basis step, you write the inductive step, and then you simply make your conclusion, which is E of n true for all n equals 0, 1, 2, ... That's it. So when you're doing an induction proof, all you're doing is the basis and inductive steps, and then you just make a conclusion. Okay, so what you do is you simply do your basis and inductive steps, and make a conclusion. Okay, and that is induction. So there you go. Now there are, these proofs vary in terms of being, in terms of difficulty. Some are much easier than others. And some are easy if you wrote them in the right way, and some are not. Like some are just easy, you just have to write them the right way. And if you write them in the wrong way, that makes them difficult. Okay. I'm going to do the ones that are in the notes, but I'm going to have a supplementary lecture where I do probably a bunch more of these just because you need to see examples, but you also need to just do proofs yourself. Okay. So this is just not a substitute for you going through the work. All right. Examples. Example 1. Let us see how this works. So what are we going to prove? We are going to prove Actually, hold on, let me see. Opening the book here because I don't know if I like what I picked for example one here. And I definitely want to make one that's not too hard for you guys. Well, that's their example one, so we'll use it. Okay. So what are we going to prove? We're going to prove this. That 1 plus 2 plus 3 plus ... up to n is equal to n plus 1 over 2 for all n equals 1, 2, 3, 4, ... Okay, so a couple things to notice about this. First of all, this one starts at 1 instead of 0, and that doesn't matter, right? Starts at 1, not 0. That's fine. It doesn't matter where it starts, as long as after it starts, it includes every number after that. So this is fine. What else can we say about it? Well, let's just get an idea of what's happening here. So like, for example, oops. Like if you check what is it for n equals 5, right? Then if n equals 5, then the left-hand side is 1 plus 2 plus 3 plus 4 plus 5. So you add those up, and what do you get? Well, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15. So that is 15, right? And the right-hand side is n plus 1 over 2. So that would be 5, 6 over 2, which is also 15. And so 15, 15. So those match. Okay, so at least for 5, it works. But, we don't want to prove it for every n, right? We don't want to go 1 and then 2 and then 3 and then 4 and then 5 and then 6 and then do it forever. We just want to be able to prove this in general somehow. So let's see how that works. So of course these match. Yeah, so I mean, that's how it goes. So yeah, let us get started then and see what our proof should look like. Proof. Okay, so for our proof here, what are we going to do? So our proof, first we need to do the basis step, right? Okay, so what is the basis step? So the way I wrote the basis step up here was that the basis step is, e of 0 true, right? And I just meant the first thing that we're supposed to show true is true. So in this case, we are starting at n equals 1, right? So that means that I need to prove this property, I need to prove this property is true for n equals 1. So you don't have to write that, but that's what I'll write. So we need to show the property, whatever it is, for n equals 1. Okay, now how do you do that? You just write it out directly. So what would the left-hand side be if n equals 1? So like for n equals 1, what would the left and right sides be? Right, that's what you should think. You don't need to write that. That's what you should think. Do I have the right color? No, I think it's this color. Show the property is true for n equals 1. So you'll see me do this a lot. I'll write LHS, and that's just like left-hand side. Okay. Left side. What's the left-hand side of this equation if n equals 1? Well, it's 1, 2, 3, 4, and you stop at n. So if n is 1, we're supposed to stop at 1. So if you write this out stopping at 1, it's just a 1. 1. Okay, now what about the right-hand side? What's the right-hand side? So the right-hand side is n plus 1 over 2. So n is 1, so it's 1 plus 1 over 2. And of course, if you work that out, that is also 1. Okay. Now, I probably should have, I know I wrote in parentheses there, show property true for n equals 1, but I probably should have written that down here too as well. I should say like for n equals 1, and then, wrote what I wrote. And so what we do is we see that these are equal, right? This and this are equal. So we can say, true, verified. So we verified it for n equals 1. So the basis step is usually that easy. If it's hard, it's only hard because it's too simple and you don't know what to write. That happens sometimes, right? Too simple and you get confused about what it is you're supposed to write to show it because it's too simple. Let's try the inductive step now. Inductive step. So this is the step where you get the, whatever the algebra is, or the real proof, so to speak. So what you need to do is you need to show what we said here. P of k implies P of k plus 1 is true. So the first thing you do is you make what we call the induction hypothesis. So you make an induction hypothesis. And I'm writing it in pink because you don't need to say that. Actually, let me say a little more. So what we're trying to do is we're trying to show this, right? We need to show P of k implies P of k plus 1. But what that means is how do you show P of k implies P of k plus 1? Well, what you would do is you assume P of k is true, and then you try to show that P of k plus 1 is true, right? You're trying to show that you can get from here to here. So you assume that P of k is true. And that's what we call the induction hypothesis. So down here, you just say, you don't write what I write in pink, you just say, assume true for n equals k. Now, what's that mean when I say assume true for n equals k? Well, that just means go up to the thing that you're trying to prove up here, and this, you're going to write it out again, but you're going to put a k where all the n's are. And then we're just going to assume that that's true. Right? So assume true for n equals k. So what is that? 1 plus 2 plus 3 plus ... not up to n, up to k, is equal to k plus 1 over true, over 2. Okay, and then the idea is for the rest of the problem, you get to use this as it's an algebraic fact. Okay, for the rest of the induction step, you can treat this like it's a true algebraic fact. Like it's true already. Okay, so you didn't prove that, right? You're assuming that it's true. What you're supposed to prove is not this one. You're not supposed to be proving this is true. You're supposed to be proving the next step is true, the k plus 1 step. Uh-oh. My iPad just locked up. Never had an iPod lock up before. All right, we'll figure this out. Hold on. It's not actually locked up, just the app. How much did I lose? Let's find out. Nothing. Okay. Um, so what are we doing? So we're assuming that this is true, and that's what we call the induction hypothesis. So you should understand those words. And then we need to prove this the next step. So it's a good idea to understand what the next step would be. I'm going to write this in pink again. You don't write it now, but you're supposed to recognize it when you get to the answer. So what would this look like for n equals k plus 1? And again, this is just for our own understanding, not what you write for a proof. So what would this look like for n equals k plus 1? Since we need to do it for n equals k plus 1, what would it look like? Well, for n equals k plus 1, it would be basically the same as what you have there. But when you write out the numbers, 1, 2, 3, right, you keep going. And where would you stop? Well, you wouldn't stop at k, right? If n was k plus 1, you would have to go one more out on the right. You'd have to add one number to the end. And then what would the right-hand side look like if you had an n equals k plus 1? Well, if n equals k plus 1, then instead of a k here, you'd have a k plus 1 here, right? And instead of a k plus 1 here, you would have a k plus 1 where the k is, and then k plus 1 would make it k plus 2, right? That's what it would look like. And so what I just wrote down is actually what we're supposed to be showing is true. Okay. So the above line is what we're supposed to be trying to prove in this step. Okay. So again, all of the pink is not necessary. It's just to tell us what we should be doing. So like you kind of do it in your head. So what you should be doing is you should be looking at this left-hand side and say, okay, well, I've got this. Now this entire line is true. Why is it true? Because we assumed that it was true and we get to pretend as if it was true. So we assume that this is true. And then what you need to do is say, well, how would I be getting from this line to this line? And what you're supposed to recognize is the simple fact that the only difference between the n equals k line and the n equals k plus 1 line, at least on the left-hand side, is that this has an extra k plus 1. That's what you're supposed to notice, right? This is extra. So when we go to do our proof, there's many ways to actually do this, but I'll do it in hopefully the easiest way. So back to the proof. Here's what you do. So let's just start with our induction hypothesis because we know it to be true. So we got 1 plus 2 plus 3 plus ... up to k equals, what was it? K plus 1 over 2. That's a true fact, so I can start with that and be okay. Now then what I want to do is I want to turn this into the k plus 1 step. So what the left-hand side is missing is a k plus 1. So I'm just going to go plus k plus 1 on the left and plus k plus 1 on the right. Now you're doing algebra here. So if I want to add k plus 1 on the left, which I do because that'll make it look like this, then you have to add k plus 1 on the right. What you absolutely do not do is you don't add the k plus 1 on the left to make it look like this, and then just start writing this on the right. You have no reason to get rid of this and replace it with this. So do not do that. Okay. You're doing valid algebra. So you start with the induction hypothesis that you know is to be true. And then I decide to add k plus 1 to both sides because I think it will help me. Let's see if it does. So I get 1 plus 2 plus 3 plus ... plus k plus 1 on the left. That's what I want. That's fine. And on the right, I just have k plus 1 over 2 plus k plus 1. Okay, so this is where I am. And so at this point, what you're supposed to recognize is the left-hand side looks fine. The right-hand side here does not look like this form or this form, right? And so of course it doesn't match this. So what you need to do is you need to do some kind of algebra here to hopefully make it look like the original right-hand side is supposed to look. So you do algebra here. Algebra. Okay, so what kind of algebra are we going to do to actually make this progress? Well, just write out this stupid left-hand side. All right. So what algebra are we going to do? Well, I mean, I can see that there are two terms here, whereas we should only have one. So I want to add these together. So if I'm adding these together, then, I can get a common denominator. So let's do that. So left-hand side, the left-hand term, k plus 1 over 2, that's fine. If I want to add it to this other one, I should make it 2k plus 1 over 2, right? Common denominator. And then now that I have a common denominator, I can add those fractions together. 1 plus 2 plus, I should copy paste that. That would be easier. So now that you have a common denominator, you can put those in the same fraction. Why won't it make a line? So you got k plus 1 plus 2k plus 1. All right. Then what I should do is I should recognize that I've got a k plus 1 here and a k plus 1 here, which means I can factor out a k plus 1. So if you factor out that k plus 1, you're going to have a k plus 1 over 2. Hold on, let me rewrite this. Okay, so you have k plus 1. If you take out the k plus 1, the part that I highlighted, you're going to be left with, looks like k plus 2. All right. So look at that. That's actually exactly what we were supposed to show, right? That's what the original theorem would be if you replace the n with k plus 1, right? If you took this and you put a k plus 1 there, k plus 1, k plus 1, it would be this pink line, and we have that pink line, so we must have done it. We did it. So that's it. That's the induction hypothesis. So that's the thing we were trying to prove. This was the induction hypothesis, and we got from the induction hypothesis to this. So this was the k step, this is the k plus 1 step, and we were able to get there. Okay, and that's the entire thing we were trying to do. So start with k plus 1 step, k step. Get to k plus 1 step. That's it. That's the entire induction hypothesis. So at that point, we are done with the induction step. And so the whole point or magic of mathematical induction is once you've done the basis step, which we have, and then you do the inductive step, which we just finished, then you just make your conclusion. So we jump down to conclusion, which is going to be what we're trying to prove. 1 plus 2 plus ... plus n equals n plus 1 over 2. For all n equals 1, 2, 3, ... End of proof. Okay, so some people don't like induction proofs because they feel like, okay, technically you did the two things you need to do, so you've done the proof, but it didn't really tell you why it was true or anything like that. So why? Like it doesn't give you a lot of insight into why a thing is true. It just proves that the thing is true. But that's fine. I mean, it still got the job done. If the job was to make a proof, we made the proof. So yeah, so that is an induction proof. Now, I think what we need to do is do another one real quick. What time is it? Hopefully I can get this done. All right, new proof. All right, so this is maybe a little trickier, I don't know. We're going to prove that 2 to the n is less than or equal to n factorial for n equals 4, 5, 6, ... Okay. Now, just a comment here. If you don't know what a factorial is this thing, right? So n factorial is 1 times 2 times 3 times ... up to n. Or alternately, n minus 1, n minus 2, ... down to 1. And there's a property that you kind of need, I think. Let me see if we're going to need it. Oh, yeah. So one property is this. So imagine you take like 5 factorial, which is 1 times 2 times 3 times 4 times 5, and then you multiply it by a 6. What happens? Well, the 5 factorial is 1, 2, 3, 4, 5, right? And then we're multiplying by 6. So if you take a 5 factorial and multiply by 6, you just end up with a 6 factorial, right? And so in general, that property is written this way. If you have n factorial and n plus 1, that's actually an n plus 1 factorial. Okay? So that's a super quick, this is what a factorial is. And we're supposed to be proving this fact about factorials. It's only true for n equals 4, 5, 6, and on. So if you try it for n equals 2, it probably will not be true. All right, let's go ahead and try to do this proof. So, proof. How does it look? Well, we know that we need to do a basis step, right? Let me just write what we're proving, right? We're going to show 2 to the n less than or equal to n factorial for n equals 4, 5, 6, ... Okay, so we need a basis step. So the basis step would just be verifying this property for the smallest thing we're checking, which is 4. So we should just verify for n equals 4, basically, right? That's our basis step. So again, just write it out. So like we got, if n is 4, then the left-hand side is 2 to the 4. And if n is 4, the right-hand side is 4 factorial. And I don't know if this is true, so I'll put a question mark over it and then just work out both sides. So what's 2 to the 4th? 2 to the 4th is 2 times 2 times 2 times 2, that is 16. And 4 factorial is 1 times 2 times 3 times 4. So that's 2 times 3 is 6. 6 times 4 is 24. So 4 factorial is 24. So I look at that, I see that that's true. And so I am done with the basis step, right? Basis steps are usually real easy like this. Okay, inductive step. That's usually where the work is. Okay, so for an inductive step, what we need to do is we need to make an assumption, the induction hypothesis, right? Because we're trying to go from like pk implies pk plus 1. So we need to assume that pk is true. So we assume the property is true for n equals k. Well, what's that look like? If we assume it's true for n equals k, then we're just coming up here to the thing we're trying to prove and just put a k there. So we just say, specifically, what we are doing is assuming 2 to the k is less than or equal to k factorial for, in 4, 5, starts at 4 because we started at 4. All right, so we're assuming that is true. Actually, I can't do 4 or 5. I can't just say that. Yeah, that's fine. So 2 to the k is less than or equal to k factorial. Now, what we need to do is somehow get to the k plus 1 step. What's the k plus 1 step look like, by the way? So if you think about it, what we need to show is this. Need to show this thing, but with a k plus 1. So it would be 2 to the k plus 1 should be less than or equal to k plus 1 factorial, right? That's what we're trying to get to. So, keep your eye on the prize here, right? This is what we're trying to end with. So let's start with the induction hypothesis as we did before. So we're going to start with this, 2 to the k less than or equal to k factorial. Now, a lot of these, you kind of, you know how to do them because you saw somebody show you. And that's what's going to happen here. So what I'm going to do is I'm going to say this. So the left-hand side here is 2 to the k plus 1. How would I turn this into 2 to the k plus 1? I need to multiply by 2. So multiply both sides by 2. So you just go multiply by 2. So you just go 2, 2. Now, what we get here is, of course, you've got, when you do, hold on, I don't like the way I wrote that, though. So we're multiplying by a 2 on the left and a 2 on the right. Okay, now then what you want to do is just kind of simplify a little bit. So on the left-hand side, 2 times 2 to the k is going to be 2 to the k plus 1, right? That's how exponents work, because it's 2 to the 1. 2 to the 1 times 2 to the k, add the exponents. Now on the right, you have this, 2 times k factorial. And you say, okay, well, we're getting somewhere because the left-hand side here looks like what we need the left-hand side to look like, but this is supposed to be k plus 1 factorial, and we do not have a k plus 1 factorial. But this is where you have to be a little bit sneaky. We've got a 2 here, right? But you know this, like how does 2 compare in size to k plus 1, right? Remember that k is 4 or bigger. So since k, because we're only looking at numbers 4 or bigger, since k is 4 or more, isn't k plus 1 just greater than 2 for sure? It is, right? And so if you use that fact that k plus 1 has to be greater than 2, then this thing right here, well, it's got to be less than k plus 1 k factorial, right? So this is being really sneaky here to add this. Um, I don't want the 2. I want the 2 to be a k plus 1. And you can add that because this is inequality. So if you replace a 2, which is small, with a k plus 1, which is bigger, then we just made the whole thing bigger. So it's still on, the side of a greater than symbol, or sorry, less than symbol to this 2 to the k plus 1. So you have to use logic like that. And again, somebody shows you this trick. Now you've seen it. So where we have now is 2 to the k plus 1 is less than or equal to k plus 1 k factorial. But then this k plus 1 k factorial is what we talked about up here about that, a fact involving factorials. When you multiply by a factorial by the next number, it becomes the next factorial. And so what happened to this here? Well, we didn't need it, right? Once I had this, I took this, realized that it was smaller than this, and then I only want this here and this here, and I don't care about this middle step anymore, this middle one. So we did it. 2 to the k plus 1 must be less than or equal to k plus 1 factorial. It's actually strictly less because of this, but I don't care. So that's the thing we were trying to prove for the induction step. So we're done with the induction step. So you can move on. You could even say like this concludes the inductive step. It's a good idea to say that. Tell people you think you finished it. And then you write your conclusion. What's your conclusion? Your conclusion is whatever you were trying to prove. So you just say 2 to the n less than or equal to n factorial, n factorial, for n equals 4, 5, 6, and so on. The end. Okay. I am gonna do more of these proofs for you, but I think this is a good stopping point for today. So yeah, homework should be up pretty much when this gets uploaded, and so I recommend that you get started on it right away. Just just to start working on it as soon as possible. All right, I will see you in the next lecture.